Hi friends, hope you are doing well. I'm Dr. Ganguly. Today I'm going to begin Math Question Bank 13 and we are going to discuss 5 questions and then we are going to solve them. So essentially these questions come from constraint optimization, multivariate optimization. Then I'm going to also discuss a simple integration and a math question. And then finally, the fifth question is going to introduce you to the concept of Fourier transforms, which is very useful in signal processing, in signals and systems, and so on. So let's start with the first question, and this is a very common question as far as interviews are concerned. And the question simply asks you to find the minimum surface area of this cylinder. And of course, you can see this is a cylinder here. It's defined by two variables. One is the height of the cylinder, which is given by capital H, and also we have the radius of the cylinder, which is given by small r. So the diameter of this cylinder is essentially 2 times r. Now, what is specified is that the volume of this cylinder is fixed. So this could be some value. So here it's given that volume is 1000 centimeter cube. Now, what we are going to do is we are going to solve this problem as an optimization problem. So the first part of this problem is to convert this problem into what is known as a math model. And this is the modeling process which is very important. So of course we know that we are going to have to minimize the surface area of this system. So if we look at the sides, there are two sides here. So each side is pi r square. So 2 into pi r square is going to be the area of the circular sides. Now if we look at the surface of the cylinder, that's going to be 2 pi r h. Now if we look at the volume, the formula for volume of a cylinder is pi r square h. So that's going to give me 1000 here because that has been specified that the volume is 1000 centimeters cube. Now I have these two expressions which have essentially converted this problem, which can be thought of as a physical problem or an engineering design problem, into a problem which is more amenable to mathematics. So let's now try to do this. Now, of course, in optimization, we have to write a function which we want to minimize, that is typically known as f of x. And here we also have a constraint. So here we have an equality constraint, and very often we use the function h of x to denote that. So here we have put the small h here, that is the equality constraint. And of course, the capital H here stands for the height of the cylinder. So now I can write these two in this form here. So the function we want to minimize, f of x, is 2 pi r square plus 2 pi r h, and h of x is pi r square h minus 1000. This is of course equal to 0. So of course here x is the set of variables for the problem. These are also known as design variables. So here they will be r and capital H, the radius of the cylinder and the height of the cylinder. So now what I do is I form something known as the Lagrangian or the Lagrange function, which is actually f of x plus lambda h of x, and lambda is known as the Lagrange multiplier. So then I expand this problem out. I get the f of x here, I get lambda, and I get the h of x here. So this is the function, and I have further written it in pink, and I have brought out to you that I have introduced the new variable here, lambda. So now this Lagrangian actually is a function of r, capital H, and lambda, where lambda is the Lagrange multiplier. So this is the function here. You can of course see it's a function of r, capital H, and lambda, because of course pi is a constant, 1000 is a constant. Now we can treat this as a multivariate optimization problem. That means it has got multiple variables, in this case 3 variables, and the way to find the stationary point and the minimum point of such a function is to set the partial derivatives to 0. Now to get the partial derivatives, we will fix one of the values or two of the values and then try to differentiate with respect to the third value. So if you want to get delta L by delta R, then what we do is we consider in this equation that h and lambda are constants. So we then differentiate this with respect to r. So we are going to get 4 pi r plus 2 pi h plus 2 lambda pi RH equal to 0. I can cancel out the terms involving 2 and pi, and so I get 2r plus h plus lambda RH equal to 0. This is one equation I have obtained in pink here. Now the next derivative I need to get is dl by dh. So sometimes people also call this dou L by dou h. You can call it in any form you want. I'm just going to call it dl by dh, where you know that it's a partial here. It's not the typical derivative where we use d like in the case of the single variable calculus problems. So if we consider here r is a constant and lambda is a constant, then of course there is nothing going to come out of this term, but this term is going to give me 2 pi r because I'm differentiating with respect to h, and this term is going to give me lambda pi r square. So this is equal to 0, so it gives me the nice equation 2 plus lambda r equal to 0. Now the third equation I get by differentiating L with respect to lambda. So this simply throws back the equality constraint to me. So this is the equality constraint we had. And so immediately I get that pi r square h equal to 1000. So I have three equations here in pink, and I also have three variables r, capital H and lambda. So I could theoretically solve this equation without much problem. Now looking at the second equation, I can immediately see that lambda r is going to be minus 2. So I can make that substitution, for example, in the first equation. So that becomes 2r plus h, and I can replace here lambda r as negative 2. So I get minus 2h equal to 0, and immediately from this equation I am able to get h equals 2r. So that's the first equation, which simply tells me that the height of the cylinder is going to be twice of the radius, or height of the cylinder is equal to the diameter for this problem. Now the next equation I can solve is this one here. So that gives me pi r square h is 1000. So again I make the substitution, h is 2r. So I get pi r square into 2r is 1000. And I can write 2 pi r cube is 1000, or r is cube root of 500 by pi. So that is the solution for the radius of the cylinder. So now let's put some numbers on this. Of course, you can also leave it like this if you are in an interview setting and you don't have a calculator. But if you are allowed to use a calculator, maybe you have one in your phone, you can easily get the value that radius is 5.419 centimeter here, and the height of the cylinder is twice of the radius, that is 10.838 centimeter. Now we can also calculate the value of lambda, which is the Lagrange multiplier from this equation. So it gives me lambda is negative 2 by r. So that comes to minus 0.36907. So this is the method of Lagrange multipliers, which is not only important in math, applied math, but also you will see this used in many situations in physics, in engineering, and so on, because in many cases we have to minimize a certain function and we have certain equality constraints. So in that case, we can always put it in the form of Lagrange multipliers. Now, if you have two equality constraints, you essentially have two Lagrange multipliers. So you will have the Lagrange function as f of x plus lambda 1 h1 of x plus lambda 2 h2 of x. So that's how you can solve all the problems involving minimization of functions and equality constraints. Now let's come to question number 2, which is the problem where you are asked to find the minimum point of the Rosenbrock function, and this is a very famous function which is given here, and this function is quite an important function. It is often used as a test function in various optimization problems, and you will see this in many optimization books and research papers also. So this makes for a good interview question. So now of course you know, to minimize this function we have to take the partial derivatives and set it equal to 0. So let's try to do that. So here I have taken this function, and just to show how to differentiate such functions, again not everybody listening to this video may be so familiar with partial derivatives, because I know some high school students also watch these videos. So let us take this f of xy and simply expand it. So again what I have done is I have used the formula a minus b square is a square minus 2ab plus b squared. So I get this here. Then I further expand it out to get this equation here. Now what I have to do is I have to take the partial derivative with respect to x and with respect to y and set it to 0. So to take with respect to x, what I do is I treat y as a constant in this expression. So y as a constant means this term will simply go to 0. This term is going to become minus 400 yx. Then you are going to get this term here from this. Then you are going to get negative 2 from minus 2x, and x square is going to become 2x. So this whole thing is going to be equal to 0. Now let's differentiate with respect to y, assuming x is constant. In this case, you are going to get this term here, 200y. You are also going to get a minus 200x squared term from here, and then all these terms are simply functions of x. So in the second derivative here, we are going to treat x as a constant, so this is all just going to be 0. So we are going to get this equation here, and it immediately simplifies to y is equal to x square, which I have put in pink here. Now we can take this equation, go back to the previous equation where df by dx was set to 0, and then try to expand this out here. So I get this equation here, and I get it by substituting y is x square in this equation. So you can see that this term is simply going to become minus 400x cube, and so there is a nice cancellation here, which makes my life very simple, and I immediately get x is equal to 1 and y equal to 1, and we put this star here to denote the fact that this is a stationary point or a candidate minimum point for this function. Now at this point you can stop the questioning also, or if the student is precautious, you can ask him or her to further continue and try to get the sufficient conditions to prove the fact that the point is a minimum point. So the previous conditions were actually the necessary conditions. So what we do is we rewrite the df by dx term and the df by dy term. Note we are not setting it to 0, we are simply writing the partial derivatives out. And now we try to calculate the second derivatives for this problem. So we get the d2f by dx2 term. So this is going to be taking this term and differentiating it with respect to x. So that's going to give me minus 400y, and this term here is going to give me 1200x square, and this 2x is going to become 2. Then I take this term here and differentiate it with respect to y. So d2f by dy square is going to give me 200. Again, remember x is going to be treated as a constant in the second differentiation. And then d2f by dx dy means I take this and I differentiate it with respect to y. So that is going to give me minus 400x. So I put it in the Hessian matrix. The Hessian matrix, if you have seen some of my previous lectures, you know that the first term here is d2f by dx square. This term is d2f by dy square. This term is d2f by dx dy, and this term is d2f by dy dx. So this is a symmetric matrix, you can show that, and then you finally put this value here, x star is 1, y star is 1, so you get the Hessian matrix at the stationary point. Now if you are somebody who wants to know more about Hessian matrix, I will leave some links at the end screen where you can check out the Hessian matrix from my optimization lecture series. So now the problem is not over. We actually have to show that the Hessian is positive definite if this is a minimum point. So what we do is we find the eigenvalues of this particular matrix. So now remember, for the eigenvalues of this matrix, we have to take the determinant of this particular system and set it equal to 0. So to do that, we get this system here, we expand it out. So 802 minus lambda into 200 minus lambda minus these two terms here. So it's always good to write out all these terms like in a proper manner so that you don't make any sign mistakes. You further simplify, you get this quadratic equation, you can solve it using the quadratic formula, and at the end we get this value of lambda. There are actually two eigenvalues here, of course, because it's a 2 by 2 system, and we see that both of them are positive, therefore it's a positive definite Hessian matrix, which means that this is a minimum point. Now this is something which is very important. Remember that whenever a matrix has all positive eigenvalues, then it's a positive definite Hessian. Now again, I'm going to leave the video on the end screen, which is going to guide you further on this math of positive definiteness and so on. This is related to the mathematics of the quadratic forms. Let's now come to question number 3. So this is a question which is typically asked in many math type of questions, especially in the Olympiad problems. It looks very simple. 1 by 4 to the power x equal to x. X is part of the real number space and you need to simply solve it for x. Now, of course, there are some people who will look at it a lot and try to solve it. Of course, one of the hints you can see here is that this has got to do something with probably 2, because 4 could be written as 2 square. So anyway, first we are simply trying to simplify this. So we'll write it as 1x, 4x equal to x. So I have simply expanded x out of this bracket. And then I use the fact that 1 to the power of x is 1. So I get this equation here. And then I further just switch the roles here. So I get 1 by x is 4x. Now, once I have this, what I do is I take square root of both sides of this equation, and after I take the square roots, I can take the right hand side and I can write it as 4 to the power x by 2. So remember, when you have something like this, I can take the x out and multiply it by half and I get this here. Now at this point, you can clearly see that if I take the 1 by x root of this, then this is going to be equal to 4. So here what I have done is I have taken 2 by x root of both sides. Okay, so I have brought the 2 by x into this side. So there is a cancellation of the 2 and 2 and I'm left with the 1 by x term. So I get 1 by x to the power 1 by x equal to 4, and then I can immediately write 4 as 2 square. So the whole point about this exercise was to reduce this system to a form where I can see a pattern match between these two values here. So if you look at 1 by x to the power 1 by x equals 2 square, you can clearly see that putting 1 by x equal to 2 is going to satisfy this system, and therefore x is going to be immediately equal to half. So you could have probably checked it out right here, that if you were to take the square root of 1 by 4, that would give you half. So half is a solution of this particular equation. You'll be surprised how many people will not be able to solve that previous problem. So sometimes simple problems are harder to solve than difficult problems. Now let us do an integral. Integrals are always a good way to check the student's knowledge of algorithms. Now it has been found that one of the reasons integration is so important, and even differentiation, is this actually lets students figure out a particular process about how to do things, and this kind of thinking is very fundamental whenever you are getting into algorithms, and nowadays most things are actually algorithms. So of course, looking at this, you know that since it involves sine in the denominator, cos in the numerator, any substitution of sin x would be useful, because derivative of that would give you a cos x. So that would hopefully simplify this expression. So what we do is we substitute u is sin x. So I immediately get du is cos x dx. And then what I can do, I can take this integral, I can simplify it, I can write root sin x as root u, I can write this cos cube x as cos square x into cos x dx, and cos x dx is going to give me du here. I'm going to substitute 1 minus u square for cos square x, because I know that sine square x plus cos square x equal to 1. I get this integral here. So now I have converted the trigonometric into the algebraic form. I expand it out because I can write this as 1 by root 2 root u du minus u square by root u du, and then I can simplify these expressions out. So if I take it like this, it becomes u to the power minus half du, and this becomes u to the power 3 by 2 du. Now if you know the formulas for integration, you can very easily write this as this form here. So u to the power minus half will become u to the power of minus half plus 1 divided by minus half plus 1, which is going to give me 2u to the power half, and this term is going to give me u to the power 5 by 2 divided by 5 by 2, which will come in this form. I further simplify it out here, I get this here, and then I put back u is sine x, and I get this equation here. I have to add the value c because this is an indefinite integral, and indefinite integrals always come with that added c, which is the constant. Finally, let's come to question 5, which is very important because there is a concept known as the Fourier transform, and that's very important in anything to do with signal processing. It's even used in GPS systems, satellite internets, and so on. So it's pretty much ubiquitous as far as electrical engineering is concerned. So here we have been given a simple function, and this function is f of x is 1 in the region minus L to L, where x is minus L to L, and this is 0 for all values of mod of x greater than equal to L. So in this region and this region where absolute value of x is greater than equal to L. So this is sometime also known as a unit pulse, and this is a function which is very important, and more interestingly it is very amenable to differentiation, or rather I should say to integration in an interview setting. So to solve this problem, you of course need to know the definition of the Fourier transform. So if we have any function f of x, then the Fourier transform of this function is given by f hat k is integral minus infinity to infinity fx e to the power minus ikx dx. So of course I is root of minus 1. Now this Fourier transform is sometimes known as spectral density. It's also related to spectrum and so on. So essentially it is very important in filtering, signal processing, and many other domains. So let's try to do this particular integration problem. Now, of course, the integral is from minus infinity to plus infinity, but we see the function has value of 1 only in the region minus L to L. Outside this region, it's simply 0. So this integral can be reduced to minus L to L. The value is 1 e to the power minus ikx dx. So actually this integral becomes quite simple, e to the power minus ikx by minus ik negative L to L, and I do the integration here and I get this particular equation or expression. Now we are going to simplify this in the next slide. So let us try to expand this out. So I get this value here. I take this 1 by I term outside. Remember that 1 by I is minus I. So I can do that. Now, of course, something like this is immediately amenable to trigonometric substitution. So I use the fact that EIX is cos x plus I sin x. I make a substitution here. So I put x is KL. So I get this term here for e to the power minus IKL. So cos KL will be there, and there'll be a minus I sin KL, because if you put negative here in x, then that will come out. And on the right hand side, I will get the positive equivalent here, cos KL plus I sin KL. Now I will further simplify this. All I did is I took the negative on both sides here. It's important to do this very carefully because very often people may do sign mistakes here. So we do that, and immediately I get a cancellation of this cos KL terms. I get minus 2i sin KL because there are two of these values, and then I square immediately is minus 1. So I get this is 2 sin KL by K. So that's the Fourier transform for the unit pulse. Now, this is one of the simplest questions of the Fourier transform, and you will start realizing once you see various things such as Fourier transform, Laplace transform, that why integrations are so important and why so much time is spent in teaching different integrations, complex numbers, and so on to the students in high school, especially if you are a high school student. So that was the video for today, and I'm going to leave some videos on the end screen which are going to give you some more information about things such as quadratic forms, positive definiteness of matrices, and so on. And certainly I will see you in a video sometime soon. If you have not seen my previous math question bank videos, do see them because I'm slowly building up this course in terms of complexity, and the way I'm building up this course is by solving examples. So it's going to certainly help you understand math, because one of the best ways people learn math is through examples. And of course, if you need any theoretical background, you can consult any typical math textbook which will help you enormously.